going to discuss about the insertion operation in binary search tree. Firstly, in binary search tree, it should have at most 0, 1 or 2 children. In binary search tree, the condition is the left subtree should always less than the root node and the right subtree should always be greater than the root node. Now we perform insertion operation. First we create a class tree node and initially we point left and right pointers to the null and we store the key value here. Okay, now we create a root. First we are going to insert an element 10. First we check the root is null. If root is null means then we are going to insert the first element itself, it becomes the root. So we call this function tree node and we create, here we store in self.value we store key element which is the 10 in our case and we return the root node. Now the key is 20. Let's check this. Here key is 20 and the root element is 10. 20 less than 10, no. This condition is failed. Then we go to then we insert this element at the right of the root node. Here we can see insert this at the root dot right and key is 20. So we insert it at the right to this element. And our next element is 9. 9 which is now this is the key. 9 less than 10. This condition is true. Now we go to this insert. We insert this 9 at the left side, so we travel to the left and here the element is 9, so we insert it left to the root. And in the same way we insert 17, 35, 50, 17 which is greater than the root. So 17 is greater than 10, so we go to the right subtree and again here we check 17 greater than 20, no. So we insert left to the right to this node. Here we insert 17 which is left. See, it obeys the property of BST. The left side trees are always smaller than the root and these elements are greater than the root node which are right elements. And again we insert 35 which is greater than 10 which is greater than 20. So we insert right 35. Now our next element is 50 which is greater than 10 and which is greater than 20 and which is also greater than 35. We insert it at the right. So this is the case here. If the element is greater than the root node, then we insert it at the right. If the insert is less than the root node, we insert it at the left, which we call this insert function recursively, and we insert the elements.
Explain how to find the minimum value node in the given binary search tree and also at the same time maximum value. We'll store the node to the current node. For example, if 10 is current, we'll check current dot left, that is 5, and we'll traverse through all the left side elements in the binary search tree. So here the minimum element will be 4. 4 will be returned here if the condition is failed. Maximum value in the binary search tree. This is also same like minimum value, but we'll traverse to the right subtree here. As in the binary search tree, maximum values are always present at the right subtree of the node. So here 10 is the node and we'll check through 12 and through 14 and we'll not check 11. As left side elements are always smaller, we'll check only the right side element. So here we will be having 14 as the maximum element. So we will return 14 here as the condition is failed. So like this we will check the minimum value of a node and the maximum value of a node. Now I'd like to explain how to find INORDER predecessor and INORDER successor in a binary search tree. So firstly, what is INORDER predecessor means? The maximum value in the left subtree is known as INORDER predecessor and the minimum value in the right subtree is known as INORDER successor. So now we'll see how to find them. So firstly, to find the INORDER predecessor, we have to go check the root. If the root is null, we have to return -1 and -1. And next condition is root dot value is equal to the element. Here we will be passing the element right and that will be checked here. If the root dot value is equal to the element, we will check the INORDER predecessor and successor for this element. Return self dot max value of root dot left, which is nothing but INORDER predecessor, and self dot minimum value of root dot right, INORDER successor. And here INORDER predecessor is the maximum value in the left subtree, that is 45. This is the INORDER predecessor. And coming to the right subtree, the minimum value is 60, right? So this will be the INORDER successor of this condition is element is less than the root dot value. Suppose if the element is not 50, we'll take 40, we'll take 40. We'll check root dot value is equal to the element. 50 equals to 40, not right. So we'll go to the next condition. Element is less than root dot value. 40 is less than 50. Condition is correct, right? So we'll return self dot. Again we'll call this function recursively with root replaced with root dot left. So we'll check 40. The left subtree is 30 and right is 45. And here we'll get the max value of the left subtree, minimum value of the right subtree, which is nothing but there are only two values here, and we'll get 30 and 45. This is how we'll find the in-order predecessor and in-order successor in a binary search tree. And we'll also go to the else condition also if these two conditions are failed. If element is greater than root dot value, we'll go to the right subtree and we'll check the in-order predecessor for this.
So now I am going to explain about the height of the binary search tree. Here simply height can be defined as the number of edges present at the longest part of that binary search tree from that particular node to that leaf node. Now here we consider it as a root node. Now from this root node we have two edges B and C. So from this if we consider to have only two edges. Consider here only C and F from A. But from here, if we consider A, C, D. So here for this binary search tree, we consider this as the longest part, which has three edges. Now here we consider this as the longest part of the particular binary search tree from the node A to the leaf node E. Now here is the code to find the height of the binary search tree. Now we declare a class node. And now we consider self dot left is equal to none and right is equal to none. And then we consider to find the main case of the height of the tree. Here we declare find height of the particular node. If node is none, means if node is none, here the subtree is empty or it is an empty subtree. If it is an empty subtree, then it returns -1. Else if the node contains a particular value or it is not an empty subtree, then we find the height of the left subtree. And again we find the height of the right subtree. Now here comes the main part. It returns the maximum value of the right subtree and the left subtree and it is added to 1. Now I would like to tell about deletion operation in binary search tree. There are three cases in deletion operation. When the root node have 0 child, that is leaf node, 1 child and 2 children. If you want to delete one, which is the leaf node which have no children, here we see root is none, which is then the tree is empty. Here the condition is tree is empty. If the element which you want to delete, the key which is less than the root value, then you have to travel to the left side of the root node and you have to delete the left side element and key which is the element you want to delete. If the key is greater than root value, then you have to travel to the right subtree and you have to delete the element which is at the right root dot right. Let's see these conditions. Now I want to delete leaf node. Then you can directly delete this link. There is no problem in such case. Now we see the second case in which the root have one child. Like if you want to delete 9, let's see. Here it consists only one child. If the root dot left is none, here there is no left side to the root node 9. Then you have to store you have to take a temporary pointer temp and you can store this root dot right which is 8. You have to store this in temporary variable and you have to make this root value as none. This points to none and you can return temp which is 8 in our case. This is the case where you have to if there is no left subtree. This is the case if the root dot left is none. Let's see if the root dot right is none. In the same way you have to store that root dot left to the temp and you have to make the root to none and you can return the temp. If now the case is where the Now this is the case where the root have two children. Let's see the case. If the root have two children, then you have to consider the in-order predecessor or in-order successor. In-order predecessor means you have to replace the root value with the maximum element in the left subtree, or in-order successor means you have to replace the root value here, which is 20, with the minimum value in the right subtree. Let's see the case. Here you have to store a temporary value which is left on middle value right subtree, which is in-order successor, which is the minimum value in the right subtree. I want to delete the element 20, so I can replace with the minimum element in the right subtree, which is 30. Now we can replace with 30, which is the minimum value in the right subtree, and you have to replace this with the root node, which is a temp, which we have stored this 30 in temp, and we are taking this temp node value to the root value, which is here we are storing 30 and we are deleting 25.
I would like to explain the code for searching a given element. For example, if the given element is 5 and we have to search it in the binary search tree. First we have to check if